cuenta con una maestría de Ingeniería Estructural de la Universidad Politécnica de Cataluña, donde actualmente hace su doctorado también, en Ingeniería Sísmica y Dinámica Estructural. Ahora él presentará Assessments and the Functional Recovery of a Seismically Isolated Hospital for 3 Levels of Seismic Hazard. Por favor, hay que darle la bienvenida de forma híbrida con una ronda de aplausos. Ok, Jean-Pierre, todo tuyo.
Thank you, Carlos. Good morning to everybody. Thank you so much for this presentation and the new opportunity for me for 3 times. This important event of Peruvian science in Europe. It's a great pleasure for me to be here again. So I apologize for not be there in person. So I had a trouble with my appointment at the consulate. So anyway, give me 1 second. I will share my screen. Okay, my topic is the following: a seismic and functional recovery of a seismically isolated hospital for 3 levels of seismic hazard. I wanted to start by showing a short video in a few collapse or totally collapse of a structure in Mexico, for example. In this video, you can see a few collapse or totally collapses important buildings like a commercial center or the hotel, or maybe the essential buildings like a hospital. In Mexico, Ecuador, and Peru, of course, are among the most seismic countries around the world. This video you can find in the social media. The video is 4 or 5 years ago, but it's a little sad, of course. I have divided my presentation in 5 parts. In the first part is the introduction. The 4 parts is the functional recovery evaluation. This is my principal topic for today. And finally, the conclusions. In the first part is the introduction. In this slide, you can see the 2 differences of kind of the collapse or the damage. In the peaks of the left, you can see the damage in structural elements, such as a beam, columns, wall, and so on. In contrast, in the peaks on the right, you can see another kind of the damage in the non-structural elements and components. Non-structural elements such as the pendant ceiling, for example, this, and the decks, and the wall partition, and the another non-structural components or element, racks, bookcase, for example. But one of the main trouble in a seismic country is not being to prepare for it, because the earthquakes are unpredictable and almost all will cause the collapse of essential structures such as a hospital or healthcare center if they don't have any seismic protection system. But for that reason, I have the first question for this presentation is that if essential structure like hospitals suffer the structural and non-structural damage, focus the structural damage is the principal behavior. For example, the columns, but no structure is the inside, the elements of inside the building. For what happened? Where do the inches and this already inside go? In this slide, you can see, for example, is of course the inches and in patches will be outside the hospital after the earthquake because the hospital maybe have a damage or maybe collapse. And then in a new earthquake, the new inches and in patches will be outside the building, outside the hospital as well, right? But in this slide, you can see, for example, in Mexico, inches and in patches in the street and the parking lot after the earthquake in Mexico. Is a little sad, right? Maybe diet because there aren't medical equipment outside the hospital after the earthquake. So what happens if you wanted to build, for example, the hospital building? In this slide, you can see the 4 kinds of the structure. For example, in a hospital, this is the price. For example, you only need to pay 8% if you wanted to construct this kind of the structure. For example, elements structure. And then 44% and 48% is only for non-structure and elements and components. So if you want to build the hospital, you need to improve the behavior first in the structure elements, being column and so on. And then the most important is to keep the good behavior in the non-structure elements and components. Components like, for example, the special machine in operation room, for example, the scanner or the resonant magnetic, for example, is so expensive. For that reason, the price in the non-structure elements and components is more important than the structure elements. So how you can find or how you can adjust, for example, the
recording in progress,
improve the behavior in this kind of the building. For example, in this curve, you have the 2 kind of the different behavior, the linear and non-linear behavior. But I don't need the able in the hospital after the earthquake. I need the able the use in the medical room or the in essential area or critical area, for example, the operation room after the earthquake. So after the earthquake, too much people in inches go to the hospital for the problem with the saddle, right? For example, I want to improve the life safety, the property loss, and the functional. This is the principal part of the research. So in the second part is the methodology. I use this methodology is the PBE or PPBE, the probabilistic performance-based earthquake. In this graph, for example, you can see the first part is the performance-based earthquake engineering. And then I have this graph. For example, in this graph, if there is an earthquake in this time, for example, tomorrow, and then I need to get the functional recovery. If there is the earthquake, I need to time for recovery the operation. For example, if the earthquake is tomorrow, maybe I need 4 days, 3 days, or 5 days after the earthquake for recovery the activities or the normal activities. This is the functional recovery, or this is the methodology I use for this event. This is my example, for example, the simulation of the building response. I use the 8-story building. The location is in Los Angeles, in US, in California. It has a height of 32 meters in reinforcing concrete of material. The peaks of the left, you can see the building in 3D. In the middle, you can see my building in 2D plane. You can see, for example, the structural elements, beams and column, and then you can see the distribution of the areas of no structural elements and components, for example, the wall, for example, the resistation and operation room. And then you can see the interface of semi-Calais isolation. This is important, or this is the principal topic for today. And then you can see the ground motion selection. I use 22 ground motion selection in each direction, for example, 22 in X and 22 in Y. The totally 44 ground motion selection for this research. But maybe you are thinking, okay, Jan, but what is the seismic isolation? What is the special device for your research? I want to share a new short video, but before I want to explain it, the seismic isolation is the special device have the maximum vertical stiffness as the maximum flexibility horizontal. So you can put this special device through the superstructural and the substructural. For example, in this video, you can see two same building, but which is the difference? The difference is in the building of the right have the interface of seismic isolation, but in contrast, the another building on the left don't have any seismic protection system. For that reason, when the earthquake starts, you can see, when I run in the video, you can see the first damage in the structural elements, columns, beams, and so on, and then you can see the damage inside the building. Why? Because the floor acceleration increase in each story. So, for example, if you have the acceleration in the first floor 0.4 G, for example, in the top or in the roof, the acceleration is increased, maybe 1.2 G or 1 something G. So in the standard, say, if you have, for example, 0.8 or 1 G of peak floor acceleration, you can get the damage in non-structural elements and components, because components is sensibility of the acceleration in the floor. But in contrast, in the another building on the right, this building have the seismic protection system with this special device, LRB. This is the name of the special device. With this interface, you don't have any damage in a structure and any damage inside the building, because the displacement is less and the acceleration is so less in contrast of the another building. I run the video. For example, the earthquake coming, look at the video on the left, and the thing of the left, sorry. You can see, for example, the damage first in the bottom and the top, and the behavior is like a pendulum, and then you can see damage first in the structure, and then the most important damage is the inside the building. For example, the bookcase and the table, maybe the ceiling if it has. But in contrast, in another building, the damage of a structural elements is 0. And then the damage inside the building is 0 as well. For example, look at this, nothing, 0. Because the concentrate, the plasticity is inside, is in this interface. This is the, this is the special device. The special device is part of the seismic isolation system. Well, In this slide, you can see the mathematical model. I use this lead rubber bearing, what is using as isolator is the most common. I use that kind of the device because it's more common around the world. This is the mathematical model in the middle of this slide. And the right, you can see my model, okay, fry model to OpenSys. I use the OpenSys. OpenSys is the software if you want to model in this kind of the building. And then I use 3 intensity magnitude for analyzing my building. I use occasionality, rare, and very rare. For example, the occasionality earthquake is the return of period is 225 years. For example, in Lima is common. Sometimes there are this earthquake or temblor, for example, is 2 or 3 times a month, every month, but it's lost. The magnitude is between 4 and 5, more or less. And then there is another earthquake. It's more strong. The return of period is 474 years. It's more strong. And then there is another earthquake. The name is maximum considered earthquake. This earthquake have the return of period is 2,475 years. But if there is, for example, in Lima, one earthquake like the return of period 475 years or 2,475 years, in my opinion, the totally damage is like 90% of the totally Lima, for example. Is so sad. And then you can see my results. For example, in the left is the lateral displacement. Keep in mind, my building have a semi-isolation. For that reason, the displacement is so less in contrast in another building without semi-isolation. In my case, my building, the lateral displacement is so less, for example, in the drift. The drift is a term in engineering. Is 0.3 something. In centimeters, is like 1 centimeter, 1 point something centimeter. It's so less. But if you don't have any semi-protection system, maybe your displacement is 30 centimeters, 50 centimeters, or maybe more, or maybe collapse. In the peaks of the right, you can see the floor acceleration. In the floor acceleration in my building with semi-isolation is so less. For example, it's below 0.4 G. In the standard says, if you have the floor acceleration in the each acceleration of your building in hospital below 0.4 G, you don't have any damage. Any damage first in the structural elements, remember, being columns, slabs, walls. And then you don't have any damage in non-structural elements and components, resonant magnetics, pendant ceiling, bookcase, and so on. In this slide, you can see my building. My building is in the left, the structural system, is the concrete, the beams, the column, with my seismic interface, my special device, and then I include the non-structural elements. Which elements? For example, the ceiling subsystem. Ceiling subsystem is in Spanish the cielo raso. El cielo raso siempre colapsa cuando hay máximas aceleraciones y pues puede matar a muchas personas. Después, and then the partitional wall subsystem or the piping, for example, the tuberías in Spanish. But if I include the non-structural element like this, and then I include another special elements in an operation room. Operation room, for example, the 4-pole or the hospital bed. This is the basic, the machine inside the building, inside the hospital building. If I run this model, I can get these results, this graph, for example. If I use seismic isolation system, of course, the damage in a structural system is 0. You can see in this graph, for example, no loss. In this magnitude is the common earthquake, the device-based earthquake, and the maximum considered earthquake. The damage is like a 0. 0 in my beam, my column, my slab. But in contrast, in my non-structural elements and components, for example, in the ceiling subsystem, I have a little damage in maximum considered earthquake. Remember, 2,475 years or return period. Maybe 18% or maybe more. In partitional wall subsystem, I have a damage in normal earthquake, the device, and maximum considered earthquake. And then I have more damage in medical equipment. In medical equipment, like a 4-pole or hospital bed. For example, in this case, in 4-pole, I have maybe 70% in damage in a rare, in the device, the design-based earthquake, sorry, and maybe 90% of damage in maximum considered earthquake. in hospital bed as well. For example, in the maximum consideration, I have maybe 40% of damage, probability of damage. The green is no loss, partial loss, and the red is the full loss. I don't have full loss because I use interface the special device for this behavior, for improve this behavior. This is the principal curve for the functional recovery evaluation. In this slide, you can see the peak on the left is the return of period for 235 years. So if I use, for example, the common or the occasionally earthquake, after the earthquake, I need 1 day or maybe 1 day, 0.5 hours for recovery the activities. So in contrast, if I use the return of period 2,475 years, I need 5 days for recovery activity. After the earthquake, for example, if the earthquake is 2 days, I need 5 days more for recovery activities. In this slide is the global functional recovery curve for both models. The peak on the left is the model without medical equipment. If I don't include the medical equipment, I need only 2 days for something for recovery activities. But in contrast, if I include the medical equipment, I need 5 days or more. So what is the conclusion? The principal conclusion for this presentation is when considering the vaccine medical equipment, recovery time increased to 1 day, 2.4 days, and 5 days for 3 seismic hazard. But an detailed assessment of the medical equipment damage is necessary for an accurate estimation of the functional recovery. That is true because if I want to achieve the improve the good behavior, I need to include more medical equipment. In this research, I use only 4 or 5 medical equipment, but I need to include more medical equipment if I wanted to get the more accurate estimation of the functional recovery, for example, for my building of a story. Hence, it is critical to develop space facility and recovery function for such equipment. So that's all. Thank you so much for your attention. If there are any questions, I'm so happy for answering. Thank you so much.
Fantastic. We have only one question for this session. Solamente comentarios, así que por favor.
Yes, short question. So, a problem when you have new technologies is to convince people is the cost. So how much increases the cost when you apply that kind of technology to something standard?
Yeah, sure. That is the principal struggle if you wanted to apply that system. For example, if you use ERV is the most common, the kind of the seismic isolation, maybe increasing the total price, maybe 2 or 3% of the total. But it's good because after the earthquake, you don't have any damage. For example, if you have your hotel or your building, for example, the resident building, not only hospital, but for example, the office. If you have the office building, if you don't include this special device, and then after the earthquake, you have a damage. For that reason, after the earthquake, you need to pay first for reconstruction, for new design, for repair, right? But if you pay for this special device, you don't have damage. You don't have any damage first in structure, and you don't have damage of your components. That is important because you save money, of course, but the price increase. 2, 3, maybe 5% of the total price, but depends what kind of the seismic isolation you use. If you use, for example, the frictionally is another kind of the seismic isolation. In my research, I use elastomeric, but there are more kind of the seismic isolation, for example, the frictional. If you use the frictionally seismic isolation, the price is more, maybe 15 or maybe 20% of the total price for your building.
Right. Thank you so much, Pierre. It was an excellent presentation. Thank you so much as well for presenting here online. We really appreciated your presentation. So again,
thank you so much for that.
Congratulations.
Okay, thank you.
Ahora, la próxima presentación será por